Okay, so welcome everyone back to the Oxford Discrete Maths and Combinatorics seminar. So as usual, please feel free to ask questions in the chat as the seminar goes on. So it's a great pleasure today to have Mehtaab Sawhney, who's going to talk on threshold for Steiner triple systems.
Thank you, Alex. And yeah, so today I'll be discussing the threshold for Steiner triple systems, and everything I'm discussing today is joint work with Ashwin, who's a graduate student at MIT with me, and Michael Simkin, who's at Harvard. And in the chat, I put a notability link. I'll update it every so often so that you can scroll back as things escape from the screen. So just for the sake of concreteness, let me define the main players in this talk. So an NQR design is a system of sets each of size q such that every set of size r is in exactly one set of size q. And as I'll be discussing thresholds, I have to be discussing thresholds with respect to some random object. And the random object we'll be considering is sort of the most natural one here, which is the random Q uniform hypergraph. So I'm going to denote this GQNP. So this is the random Q uniform hypergraph. Where every Q edge is included with probability P. And notice that when Q equals 2, this is exactly normal GNP. And so, given these two definitions, I'm already able to state sort of the main topic of interest today, which is for what P does the random Q uniform hypergraph have within the set of sampled edges? Does it have a NQR design in the subset? So for what P, can one find and in full generality, I expect this question to be quite hard because this question implicitly contains many sort of questions which themselves have been of significant interest and significant work. So just so we're on the same page. So even the deterministic question here is a rather famous result. So P equals 1. So this is just saying, okay, there's no sampling going on. You have the set of all possible Q tuples at your disposal. This is asking for the existence of designs. And until 10 years ago, this was open. For Q and R moderately large integers, it was not known that there exists a single NQR design. But now, due to breakthrough work of Peter Kibosh, we now know that NQR designs exist for n sufficiently large as a function of Q and R, subject to some divisibility constraints, which will come up later in the talk. And so this is based on a method called randomized algebraic constructions. And then there was a subsequent second proof, which will be more closely related to the techniques in this talk by Glock, Kuhn, Lowe, and Ostis, which use this method of iterative absorption, which will make an appearance later in the talk. But even in cases where sort of the existence of the corresponding design is trivial, this is an interesting probabilistic question. So in particular, sort of the simplest design is when Q equals 2 and R equals 1. And if you do some unwinding, an N-to-1 design is the exact same thing as a perfect matching. And to see this, let's just write it down explicitly. So the sets of size 1 are the vertices, and each edge is a set of size 2 covering those vertices. And since the perfect matching, you're covering every vertex, and you're covering every vertex exactly once, since it's a matching. And then the question that this is asking is, when does GNP have a perfect matching? And so so it turns out that this was solved actually in essentially the original work of Erdős and Renyai on sort of defining GNP. And so they proved that at P, which is roughly log n over n, that you have a perfect matching. This was in 66. And this was later improved to a hitting time result. So although we won't be discussing results of this precision, it's a beautiful theorem, so I'll state it more precisely. So you can look at your random graph, and at the first moment where so there's an obvious obstruction to having a perfect matching, which is you need every vertex to have some edge coming off of it. And what you can say is look at the process where you sort of put edges down one by one. A hitting time result says the first time that you have an edge, every vertex has at least one edge coming off of it, then you have a perfect matching. And this turns out to be true with high probability in the random graph model. And this is a result due to Bolobash and Tomasin. But it turns out sort of any other case of this question is substantially harder, even when the existence of design is trivial. So the case where Q is general, but R equals 1. So I'll just consider Q equals 3, although the ideas aren't any different. So now we have a random 3 uniform hypergraph, but we want sets of triples which cover all the vertices. And the question then becomes, let's say, when does G3 and P contain a 3-1 design? And this sounds like a really innocent question the first time you see it. I mean, somehow all we did was we took the natural graph question, we took some natural analog of a perfect matching, and we asked what is the corresponding threshold. But it turns out this is it was a very hard problem, and it's kind of infamous, and it went under the name of Shamir's problem. And just for a bit of context of why this is hard, there's no analog of Hall's theorem as soon as you go to a hypergraph. And Hall's theorem is kind of what's the driving engine behind the case in the perfect matching when you're doing the perfect matching result. And so this was a much harder result. And so first there was a result for the threshold up to a constant, which is that if P is larger than C, some constant log n over n squared, then you have a 3-1 design. And this is in this seminal work of Johansen, Kahn, and Vu from 2008. And now we know even more precise results due to difficult work of Jeff Kahn. So now we have a sharp P. So I'm not going to write down what the sharp P is, but the sharp P corresponds to where you have that every vertex has at least one triangle coming off of it. And not only do we have a sharp P, we have a hitting time result. So these are in works due to Jeff Kahn. So there's a first paper which gives the sharp P result from 2019, and then the hitting time result in 2020. And so the main result of this talk is one other case in this hierarchy up to a subpolynomial factor. So the main result is so let me state the theorem precisely. This was mentioned before. This is joint work with Ashwin, myself, and Michael Simkin from this year. So there exists C greater than 0 such that if I look at a random 3 uniform hypergraph where you have to allow n to be either 1 or 3 mod 6, I'll explain why that is in a second. The probability that the corresponding random 3 uniform hypergraph, where I sample edges with some ugly factor x of c log n to the 3/4 times n inverse, contains a 3-2 design. This equals 1 as n tends to infinity. So there are a couple easy remarks here to make. First, it's not so important what the subpolynomial factor is. The main point of the result is that this is it's subpolynomial. And second is, what do you expect the true threshold to be? So notice that in N3-2 design, so this is a covering of the set of pairs with triples. So there are, let's say, approximately n squared pairs, and each triple is covering 3 pairs. So you need roughly n squared edges. So this forces P to be at least 1 over n. So that's why we know it's sharp up to a subpolynomial factor. But in fact, you know that P has to be greater than something like log n over n. Because of coupon collector. Because in order for you to have a Steiner triple system, you need the property that every pair of vertices is in at least one triangle. So due to coupon collector, you pick an extra log n. And a kind of amusing corollary of these facts, the reason I state the second one is that there's a result of Friedgut, which says for any hypergraph property, so something that's, let's say, so the property of containing a 3-2 design is invariant under, if you take your randomly sampled set of edges and you like permute all the vertices, then the property of whether you contain a 3-2 design is sort of invariant under the symmetry. So a result of Friedgut implies that the property of containing a 3-2 design has a sharp threshold. So to be precise, what Friedgut's result states is that If you have a coarse threshold, then your threshold sequence has to grow like something like n to the alpha, where alpha is a rational number. But we know that p is at least log n over n, and it's at most some subpolynomial times n to the minus 1. So this implies you have a sharp threshold sequence with our result. And so given that, I've stated the result. Are there any questions so far? Okay. If not, I'm going to sort of dive into the proof and maybe some of the difficulties. But probably the first remark that's in order is our proof relies on these sort of recent breakthrough results regarding what is called the fractional expectation threshold. Versus the threshold. So these are results which somehow give you control of the threshold for general monotone properties via certain potentially easier to control quantities called the expectation threshold. So this was proved by Frankston, Kahn, Narayanan, and Park. And as has probably not escaped many people's attention, there was a recent breakthrough which sort of allows us to remove this word fractional and establish the full expectation threshold versus threshold conjecture. This was in recent work of Park and Pham from earlier this year. This conjecture also goes under another name, the Kahn-Kalai conjecture, probably better known as that. But we'll really be using a sort of variant of, or an equivalent restatement of the fractional expectation threshold. And that turns out to be like technically much easier to work with for our result. And it's the following reformulation of the fractional expectation threshold result. So this is, again, work of Frankston, Kahn, Narayanan, and Park from 2021. So for this, you fix some hypergraph H, and its edges are collections of sets of some ground set X. So then you say, then a measure mu on H is called Q spread. If for all S as a subset of X, you have that probability that a random sample from your measure mu contains the set X is at most Q to the S. And you have the property that you're actually supported on H. So the probability that the sampled edge lies in your set hypergraph, that's equal to 1. So it turns out, so if H supports a Q spread measure, then a random subset of size KQX times log X contains an element of X with high probability. So what this result morally states is that I fix some hypergraph. If I can construct some measure on its set of hyperedges, which is well distributed, then I can find, this gives me a good bound on the threshold. So I stated this with sampling a random uniform set of size kqx log x, but sampling a set of that size or sampling every element with probability q times log x is roughly the same. So this is some way of bounding the threshold. The way this result is stated may seem a bit tricky to use, but I think it's an extremely powerful result. And so the first thing I want to do is sort of give an example of how one applies this. And for that, I want to give a proof of Johansen-Conveaux. So there are results from 2008 regarding containing a 3-1 design. So first we need to define our ground set X. So X is just going to be the set of triples of N. And so now we need to define our hypergraph. Well, we want to contain an element of our hypergraph, and we want to contain a 3-1 design. So H is just going to be the collection of 3-1 designs. And so I have my 3-1 design, and I want to understand what measure should I put on this hypergraph. Well, notice that every 3-1 design is sort of isomorphic to every other 3-1 design up to a relabeling of the vertices. And because of that, there's sort of a natural measure you should put on the set, which is mu is just going to be uniform on the collection of 3-1 designs. And so now we just need to verify this spread condition. And that's a easy enough computation. The reason is that, well, you can sort of compute everything exactly. So we want to understand the probability some set A of 3 edges is included in our random 3-1 design. So I have to specify a set of triples A. And notice if that they're not vertex disjoint, then they can't possibly be included in a 3-1 design together, because by definition, these are vertex disjoint triples. But if they're not vertex disjoint, well, then there's some subset, and you can just count the number of 3-1 designs that extend A and divide by the total number of 3-1 designs. So, I mean, this is just elementary counting. Let me just write out what it is exactly. And if you just work it out, this is at most C over N squared to the size of A. So this gives us a measure, which is C over N squared spread. The size and roughly the probability corresponds to Q times log X. So this is like log N over N squared. And that's exactly the result of Johansen-Conveaux. And that's the whole proof. I mean, this is somehow in almost one line calculation given the result. So this is an incredibly, I mean, the original proof was quite hard and it's a difficult piece of work. I mean, this is it gives a very short proof result. And so, I mean, the proof of the main result, to be a little bit cheeky, is there exists a measure mu, which is x of C log N to the 3/4 times N inverse spread supported on STSs. And so this is really somehow, I mean, that's the proof, but the whole game is constructing this measure. But there's something I want to point out here. This is somehow, we're no longer thinking about thresholds. This is really a question of, can you construct a set of Steiner triple systems which are well spread out? And it's not exact. You no longer need to fight. If you have access to very powerful results, you don't need to directly think about thresholds. And you can think about sort of constructing spread measures instead. And so it's a powerful perspective. So the first attempt would be, well, let's try to replicate what we did above. So why can't we just take mu to be the obvious thing? So mu to be uniform on the set of STSs. So the reason this is not possible is that, or it currently appears to be not possible, is that we don't really have that good an understanding of the number of STSs. So if you write this out, we would need to understand something like the ratio of the number of STSs containing A over the number of STSs. And even for the denominator, the best result is a multiplicative, has multiplicative x of n squared minus delta factor. And this is difficult work of Kivosh, which itself was resolving an old conjecture of Wilson. So we don't, not only do we not know the number of STSs that well, we really know up to a multiplicative factor, and even that's hard. And you would need to know this for like STSs containing a subset. So this appears hard. So the thing we actually do is we somehow specify a way of constructing a random STS, which by construction is somehow well spread. And for this, the starting point is sort of Barber, Glock, Kuhn, Lowe, Montgomery, and Ostis. So this is a set of work, some of it being on these designs and some of it being on sort of finding triangle decompositions of graphs of high min degree, and sort of roughly they give a very nice way of constructing a Steiner triple systems by somehow localizing vertex sets as you go down. So I won't be able to say too much more about the method, but sort of the key output of this for our result is the following proposition from our work. So you fix some set X of your set of vertices and assume X is not too small and not too large. It's not so important what these are. And you have some sub graph of your whole graph, which is extremely high min degree. In particular, you're missing at most like n over log n edges at any vertex. Then you can look at this graph. So if you look at this graph and you sample triangles with probability x times, say, log x to some power, with high probability, one can cover all the edges of G outside of X only covering a few So what does this mean pictorially? So initially I have my whole graph G. So, okay, I'm probably going to start doing this abuse where instead of thinking of the Steiner triple system as a collection of sets of vertices of size 3, I'm going to think of every set of size 3 as a triangle in a graph. And then a Steiner triple system naturally corresponds to a triangle decomposition of the complete graph, where any two triangles in your triangle decomposition are edge disjoint. And so what this is saying is I can cover everything outside. So I can cover all the edges outside of X and let's say an edge with one endpoint in X using triangles of some density, X to the -1 times log X. So basically proportional to the smallest size. And I cover everything and then I leave X sort of mostly uncovered. So somehow if you iterate this, let's say, this procedure again and again, and you were only concerned about constructing designs, then you could sort of localize this set of missing vertices down to a very small set. And then what you can do is you can plant some sort of object initially, which lets you clean up the small number of remaining edges. And this is sort of at a high level, the idea of the existence of designs by iterative absorption. But for us, there's kind of a big problem because as X gets smaller, the sample probability is getting worse. So if X is a constant, the sample probability is a constant. And somehow you want X to be as large as possible to get as good a spread as possible. Just sort of a tension. So this iterative absorption is sort of forcing you to go down versus what you want to do is you want to go out. And you sort of want X to be as big as possible. And sort of maybe the key idea in this work is to sort of give some sort of bootstrapping scheme which lets you make X bigger and bigger. And so during the last maybe 15 minutes, I'll discuss how one does that. So is maybe the setup clear so far? If there are any questions, might be a good moment to take it. Okay, if not, so let me state what we're going to do. So the idea is somehow to do induction on the parameter of how well you're sampling the triangles. So I'm going to define a theorem, eta k, which says if G has, let's say, basically it's almost complete, and one samples triangles of G with probability, let's say, n to the -1 plus eta k, then one has an STS with high probability. And just for clarity, the case where eta k equals 1 is just saying that if you have all the triangles, then you can find an STS. And so this, for instance, follows by work of, let's say, Kivosh on his work on the existence of designs. But earlier works also suffice. So roughly, so I'm going to at some moment need to invoke this proposition. So I'm going to do is I'm going to set aside some set X and some set on top of it Y. And so step one is I'll sample triangles between X and Y with probability 1 over the size of X plus the size of Y. This is this probability. I'll explain where this probability comes from later, and keep the edge disjoint ones. So okay. So I have some set of triangles which are covering some number of edges between x and y. Okay, so then by my earlier result regarding iterative absorption, I can cover everything outside of x with density or with spread sort of x to the -1 plus little 1. Okay, so I've covered everything outside now, and now I'm just left with x. Well, I told you I have to do induction, so at some point I need to invoke the inductive hypothesis, or step 0. So step 3 is I'm going to cover x using triangles of density x to the -1 plus eta k minus 1. So now I've covered everything outside, and I've covered everything inside using these triangles, but the density is too high. So I want to go from a parameter eta k minus 1 to eta k, but notice that I'm these triangles I've used at step 3 are too expensive to me because x is smaller than n, so this density is too high. And so the key point is you can there's one funny step in this construction. I set aside these initial triangles and I need to use them somewhere. And step 4 is use step 1 to flip out triangles in x. And so I need to be a little bit more precise here. So this is best done with a diagram. Regardless, okay. Well, I've managed to mess it up twice, but okay. Regardless, roughly the point is you take this cycle in the center and you create two suspensions on top of it. And if the cycle is of even length, then there are two different triangulations. There's one corresponding to the squiggly line and one corresponding to the check marks if the cycle length is even. I've managed to draw it odd. That's the issue. So now what I look at is a triangle in the bottom. So I have these triangles in X and I want to flip them out. So what I do is I look at these configurations where every single other vertex is in Y. And if I have my bottom triangle in X and I have this configuration in Y where all the squiggly triangles are sampled in step 1, I use these structures to flip squiggly triangles for the checkmark triangles. And notice that the reason that I can do this is that the squiggly triangles and the checkmark triangles, they use the same set of edges. So by doing this procedure, if I can do this simultaneously for every triangle I sampled in X in a way that makes all these constructions edge disjoint, then I still preserve the fact that I'm a Steiner triple system. And this somehow lets me take the triangles at X and imagine Y, for instance, is the whole set. I'm somehow spreading the triangles out from inside X to away from X. And somehow negates the fact that I localized to X in my previous, as part of my construction. Somehow this lets me increase the spread of the construction. And now there's a couple of computations that need to be done. The key reason this works out is sort of, so in step 2, I sort of use these triangles. So this forces that the spread is at least something like x to the -1 plus a little 1. And if you stare hard enough at this construction, it turns out the worst triangles are kind of the check triangle, which is x, x, y. And if you do a bit of computation, its spread is something like, if you work it out, something like x to the eta k minus 1 over n. And so then you pick x to be the right size. I think following these computations is not that important. What ends up happening is that if you run this construction carefully, what you find is that this parameter eta k goes, sort of has the following nice recursion. So you can start at eta k minus 1, and eta k is eta k minus 1 over 1 plus eta k. And the point is, if eta k minus, so eta 0 is equal to 1, then you just work it out. Eta 1 is a half, eta 2 is a third, and this converges to 0. And sort of this inductive construction lets you sort of increase the spread at every stage of the induction. And that's ultimately what lets you prove the result. And that's all I had to say.
Okay, thank you very much for a fascinating talk. Let me ask if anyone has any questions. Actually, let me start first. So this was for Steiner triple systems. If you want to increase the size of your edges, which bits of the proof go through, and where are the obstacles?
So there are a couple of obstacles. So the first is this diagram I drew down. It exists for Steiner triple systems, and it's not clear that it exists for more general designs. And so how many, like, basically this amounts to how many edges how many triangles you need to create something with 2 triangulations. It seems like for higher designs that doesn't work so well, but there's actually a more fundamental issue, which is this. It's a little bit difficult to explain, but roughly what happens is when you contract your vertex set from this size to this size, and then you sort of spread everything outwards, you need that these configurations you find are edge disjoint. And this sort of prevents the spread from becoming very small. When you and if you work it out, the bottleneck is it's something like n to the -1. And for more general designs, you expect the threshold to be way lower. So it's a little bit unclear, sort of. It seems like the sort of randomized algorithm that is very spread out is a good strategy, but it's unclear how to get it to the sharp threshold for more general designs. Yeah. And
for Steiner triple systems, where do you conjecture the sharp threshold?
Yeah, it should be at the moment every edge has a triangle in it. Yeah. I don't see any obstruction. I mean, for line squares, you can prove the same sort of result we have. So it doesn't appear that there should be any other obstruction as far as I can tell. Also, the fact that you have a sharp threshold somehow suggests that there's some event like this that's controlling it.
Thank you. There's a question from Zach Hunter in the chat. Mehtaab, can you see the chat, or shall I read it?
Yeah. So that's exactly the point. So this fact that you're switching out triangles is that you want to sort of dilute the impact. I mean, sort of one easy way, maybe another way to think about spread is somehow, if your spread of parameter q, then it kind of looks like you came from a random you sampled every hyperedge with probability q. And if you have too many triangles on a small set, then that sort of gives you a certificate that you're not coming from that random system. So yeah, that's exactly the point. Sort of like this is one way of removing that bias.
Okay, any other questions? Okay, in that case, let me invite everyone to unmute.